Okay, and in the final part of this section, we'll discuss whether electronic stopping power can produce damage in materials. First of all, for metals, there is a simple rule. The electronic stopping power does not produce damage. And the reason is that the free electrons, they can move fast enough that even though there are, of course, electronic excitations, they compensate for any excited states, and there isn't time to put atoms into motion, which would produce damage. And this is true in all pure, well-conducting metals. Semi-metals or complex metal alloys may be an exception. However, if you have an insulating material, there can be certainly damage, and at least by two different mechanisms. And that is, the first one is by single electronic excitation, that an electron excited by the ion as part of the electronic stopping power can travel far from the ion path and get charged somewhere else, and this charge changes the charge state of the lattice ion, and because it's an insulator, the electron can't travel further, so you will have the electron may get tapped there, and this can be an exciton or induce bond breaking. The second is multiple strong excitations by swift heavy ions, and we'll talk more about that in a moment. So these single electron excitations, they are actually not fully understood even today, but there are some mechanisms which are at least qualitatively understood. And the simplest one is rather simple to know if you remember your basic quantum physics of quantum chemistry of covalent bonding. That if normally when you have a covalent bond, you of course have a potential well which represents the bond energy, but when an electron comes in, it may kick away an electron in this bonded orbital into what's known as an antibonding orbital, a repulsive state. This is true even for a basic hydrogen atom, and in the typical standard introduction to quantum physics, when you derive the electronic states of the hydrogen atom, you found that there is two basic states, hydrogen molecules of the H2 molecule. There is a bonding and an antibonding state. And this is also true in more complicated materials. There are generally actually a huge lot of antibonding orbitals, and if you put an electron into the antibonding orbital, you get a repulsive interaction, and if the electron doesn't de-excite fast enough, then this repulsive interaction pushes the atoms apart, and one can break a chemical bond. And this of course can lead to damage in the material. And this is important in insulators, but especially important in molecules and in organic materials because they are light, there is fraction of electronic stopping is in any case big, and these electronic excitations can then lead to damage. But there is also another class of electronic damage with the swift heavy ion track regime. And here the simple naive picture of swift heavy ion damage would be that, okay, if you have a heavy ion, it will go through the material, it will excite electrons in many atoms because it's large at the same time, kick out electrons from there, and then you could get a picture where you have suddenly many positively charged ions in a lattice close to each other. Of course, positive charges repel each other, so you could have a what's known as a Coulomb explosion, a strong repulsion of these positively charged cores. So this would be the simple way to understand swift heavy ion damage. However, it seems that these Coulomb explosions are actually not very important, that the neutralization is too rapid, and this Coulomb explosion is not the main reason to damage by swift heavy ions. Well, this swift heavy ion damage, it was already mentioned in the previous section, and as a reminder from there, we know that from the stopping power, if you're above a certain threshold, you can start getting the ion tracks, and this is especially strong with the stronger the electronic stopping power is around the Bragg peak. And in this regime, the high energy regime, the ions travels more or less in a straight path, or most of the time it travels completely in a straight path. These two illustrations are from stream, actually showing in the low energy regime 1 kV per nanometer stopping power. You have still recoils, nuclear recoils, so the ion can easily change direction. Whereas if you are really in a high energy 10 kV per nanometer, the ion travels straight. There's very little nuclear collisions because the nuclear stopping power goes down, but there is lots of electronic excitations. And another way of saying that there are lots of electronic excitations is that you reach a high electronic temperature. And as said, the simple picture of Coulomb explosion does not seem to be sufficient to understand the damage. But instead, what does seem to work quite well is what's known as a two-temperature model description of lattice and electronic excitations. So the idea is that the swift heavy ion is the source storm for electronic temperature, and then it first heats the electrons, and you get an electronic heat conduction equation. And this is the same equation as what was given before for electron-phonon coupling. And then via the electron-phonon coupling, the coupling term here, which is the same as here, this electronic excitation transfer energy to the lattice temperature, so the lattice becomes hot, and this hot lattice can then produce damage if you exceed the melting point of the material. And what's also important to understand here is that because the ion is very swift, it has a very high velocity, the ion itself actually passes through any lattice region extremely fast. Typically, if you take a few nanometer segment of the material, just calculate from the velocity, you realize that the ion itself goes through in something like 0.1 femtosecond. So the ion basically ion itself has passed the region before any atomic motion has occurred. But it heats the electrons. These electrons lead then to an electron cascade and energy deposition to the lattice, and then this can lead to the atomic motion and restructuring, which may lead to the ion track. And this motion time, atomic motion time scale is of the order of picoseconds or more. As I said, and as you realize, it's easy to understand that if the lattice becomes hotter than the melting temperature for a long enough time, then you can melt the material. In a crystalline material, this may cause damage if the molten region doesn't have time to recrystallize. And this is indeed the case, and one get these ion tracks, which are visible as ion tracks in microscopy experiments. Here this scale is 50 nanometers, so here they are in this particular picture of the order of 50 or 100 nanometers, but this is actually a cross-section. In reality, they can be microns or even tens of microns long. The radii, on the other hand, are in the nanometer scale, typically something between 3 and 10 nanometers. This is one high-resolution electron microscopy experiment where you see each atom, individual atom. Here you have the perfect crystal, and this region here is a cross-section of the ion track, which, as you can see, has roughly a diameter of 10 nanometers in this particular case. And here is a molecular dynamic simulation implementing the energy deposition from the ion tracks as lattice heating, which generates damage here. You see what happens here. You see the heating, you see the atoms are put into motion. This is in quartz, and it looks very disordered for a while, but the left and right part are actually not molten, so they retain their crystalline structure, but you see that the center amorphizes. And this kind of simulation can actually agree very well with experiment. This example is one of the first simulations where molecular dynamics simulations were compared with experiments. Later on there have been follow-up works which have given even better agreement than what is shown here. But one thing which is maybe not so obvious is that the track is actually under delts. So there is a range of studies by small angle X-ray scattering which shows the small angle X-ray scattering signal. It's actually a bit difficult to deduce. One can only say that there is an underdense core and an overdense track. These atomistic simulations then give a somewhat more detailed picture of what the radius and track core track core is. So the track core is the underdense region, and then there is a shell which is an overdense region. So this was a brief introduction to ion tracks. They will still be mentioned a couple of times during the course. I'll just mention that these track cores, even though it may seem like a somewhat exotic technology and you need a high energy accelerator to make them, they actually have industrial applications. One is a very standard technique if you want to make nanoporous filters from polymer foils. This has been done already for a long time. You can even use proton irradiation. The protons are not swift, but they still manage, protons are not heavy, but they still manage the electronic stopping from protons manage to break bonds in organic materials, which can be, and then these broken bond regions can be etched away and one can get nanoporous filters. And one can use them in lithography, at least, but by making very long tracks. This is a sort of an extreme example of almost 100 micrometer long tracks, which have been used to modify a material and make high aspect ratio structures in materials. And finally, once you have pores like this, if you wish, one can use electrodeposition techniques. Now you don't have to care about the details, but basically by taking film with the ion tracks, you can then, by putting it into an electrochemical cell, you can fill them with metal ions. And then after that, after you fill them with metal, if you etch away the polymer, you can get nanorods of a well-controlled length. And because the track diameter reduces, one can even make very sharp ticks like what is shown here. So this was the final part in this section 3, and this is a reminder of what you should have learned from all of this section. I won't read it loud, but I'll let you read it here. And if you think you don't remember any of these, please go back and read again or listen to the video again. Thank you for this section.